Hello everyone, the problem that we're going to look at today is 6.24 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. The problem is stated as follows. It says, consider a laminar boundary layer developing over a flat plate and the flow is incompressible. And the first thing we're asked to do is we're asked to substitute equation 6.31 and 6.32 into equation 6.38 to determine the boundary conditions in the dimensional form associated with flow over a flat plate of length L. The second thing we're asked to do is substitute equation 6.31 as well as 6.32, as well as the definition for Reynolds number L, which is the Reynolds number over the length of the flat plate, into equation 6.35 and compare the resulting expression with equation 6.28. And we're also told to note that for a flat plate, dp dx, so the difference in pressure over the x dimension, is going to be equal to 0. As well as u infinity, which is the free stream velocity, is just going to be equal to v, or our velocity over the plate. So the things that are known for this problem, we know that it's going to be a flat plate. We're told that it's going to be laminar flow, and we're also told that it's going to be incompressible flow. And so in problem A, what we want to find is we want to convert the non-dimensional boundary conditions to dimensional values. And then for problem B, we need to convert 6.35 to the dimensional form and compare it to 6.28. Our schematic is going to look like this. So we're going to have our free stream velocity, u infinity, and it's going to be flowing over a plate. And we're going to be developing a boundary layer over the length of that plate. The assumptions that we're going to make is we're going to assume it's two-dimensional. So we're just looking at a 2D slice of the plate. We're going to say that there's no pressure gradients across the plate, as well as this condition which was given to us, which is v, the flow velocity is going to be equal to the free stream velocity. So in problem A, the equations that were given in the book are 6.31, which are the non-dimensional forms of our spatial dimensions, so x star and y star, which is just x over L and y over L, as well as 6.32, which is the non-dimensional velocities in the u and v direction, which again is just going to be u over v as well as v over v. And 6.38, these are actually going to be our non-dimensional boundary conditions. So we can say u star at x star and 0 is going to be equal to 0. So this is along the wall. The velocity is going to be 0, or also known as a no slip condition. And then for u star at x equals infinity, so in the free stream, it's going to be the free stream velocity times the x star over v. So if we substitute 631 and 632 in a 6.38, we're going to get these two equations. And when we simplify them, we'll get our dimensional boundary conditions. And again, they're going to tell us the same thing. So at u, x, comma 0, we're going to see that at the wall, the velocity is going to be 0 or no slip. And then at ux is equal to infinity. So as we move up in the y direction, we're going to achieve our free stream velocity, or v. And so for problem B, what we're going to do is take equation 6.35, which is given as this equation, which again is the non-dimensional form of the momentum equation. And when we substitute in all of our equations from the previous problem and convert our u star non-dimensional form to dimensional form, we're going to get this equation, which is u du dx plus v du dy is equal to nu, the kinematic viscosity, times partial squared u over partial y squared. And we can now compare that to equation 6.28. And when we zero out this term, as we know, there is no pressure gradient, so this entire term here is going to go to 0. We're actually going to get the same equation. So all this is showing is that we can actually convert our non-dimensional form to a dimensional form, and the equations are going to be the same. So depending on our problem, we can actually use either form of this equation and we're going to get the same answer.